by Richard Turner, who's a member of Prof AI based at Cambridge.
Okay, great. Thanks, Paul. Thanks for the introduction. Yeah, so I'm delighted to present our work on end-to-end data-driven weather forecasting, and very appreciative of the invite to kick things off. So, as Paul said, I'm the sort of Cambridge lead for the Prof AI Hub, but this work happened sort of before that, actually as part of an EPSRC Prosperity partnership between University of Cambridge and Microsoft Research. But we've been carrying on that work within the hub, and also in my role at the Alan Turing Institute, where I'm the research lead for AI weather forecasting. And Turing came in and very kindly provided us with much of the compute to get us over the line in this project, which we're extremely appreciative of. So let me just start by setting the scene. So we desperately need better environmental prediction tools. For instance, we don't have to go back very far to the flooding that happened in Texas early in the year, where 134 people lost their lives, or before that, back to autumn time last year, where we had the floodings in Valencia in Spain, where another 230 people, over 230 people lost their lives. Wildfires in LA in between, causing $250 billion of damage. But this problem, of course, is not limited to the Western world. A year ago in Southern Africa, there was one of the largest droughts for the last 5 years, where 60 million people needed assistance in Southern Africa. In India, over 1 million people lost their lives due to severe air pollution events last year as well. So across multiple of the Earth systems, across multiple timescales, we're in desperate need of better prediction systems. This isn't just limited to, early warning systems. This is also for agriculture, for the economy, for supply chains, et cetera, et cetera, et cetera. Everything sort of hinges on good predictive models for the Earth systems. And for roughly 100 years, those systems have worked in the same way, using big physical models. And they are triumphs of science and engineering that have been increasing their accuracy steadily over the decades. But that progress is relatively slow. And as we're faced with a changing climate, with these disasters getting worse and worse year on year on year, we sort of need to make better progress. It's also out of reach for many of the nations on the Earth. For instance, if you're in Africa, it's hard to run one of these big physical models, which I'll talk a little bit more about in a second. And so we sort of need a way of rolling out these systems across the globe. And one of the ways to do that, I think, will come through deploying AI systems. So I'm going to give you a little bit of the background for how forecasting currently works across actually multiple of the Earth systems here, but I'm going to use medium-range weather forecasting as a sort of prototypical example, but exactly the same thing is happening, say, for atmospheric chemistry forecasting or for oceans, et cetera, et cetera. So take this as like the canonical sort of practice in this area, which serves as like an example for these other application areas as well. So medium-range weather forecasting means predicting the weather up to from about a day ahead to about 2 weeks into the future, and it's obviously super important for many of the reasons that I just mentioned. How does this work currently? If you go to one of the best operational services, say European Centre for Medium-Range Weather Forecasts in Reading, well, they start with an estimate for the current state of the atmosphere. So that's what's shown over here. So this includes sort of a grid laid down over the Earth at multiple different pressure levels or heights through the atmosphere, and a description of what the variables are at each of those locations. So think temperature, wind speed, humidity, pressure, et cetera, et cetera. So you start with that initial state of the atmosphere, and then you're going to evolve it forwards to some time step delta in the future to produce what's called the forecasting step of weather prediction. And in practice, what does this involve? Well, it involves a very, very complicated set of coupled PDEs, which are run on this very fine grid, roughly a 10-kilometer set of grids across the entirety of the world. And this is page 10 of about page 45 of ECMWF's description of that big physical model. It's run with a 12-minute time step, and it involves about 9 million lines of code that, as I say, have been developed over many decades. So it's incredibly costly. It's really expensive to run. Requires a supercomputer. Requires a large team. It's quite hard to innovate because it's got this huge code base and some technical debt in there, and it's out of the reach of many organizations or countries. That said, it has steadily got better year on year on year, and is a real triumph. So that's the sort of the first step of forecasting. The second step is to incorporate observations. So as we go along, we observe information from ships that go across the ocean about things like the temperature of the atmosphere. We have measurements from radio sonder on weather balloons, which are going up and down the atmosphere. We can direct planes to go and sense in various areas. Obviously, we have weather stations, and of course, we have a ton now of remote sensing data. And as time goes by, we accumulate updated information from these. And so there's a second step, which takes a recent forecast and assimilates this new observational information with the forecast to produce an updated estimate for the state of the atmosphere. For those of you who know about Kalman filtering, it's very similar to like the Kalman filtering update. This is also incredibly expensive. In fact, it's just as expensive as the forecasting step, and still requires a large team and a supercomputer to carry it out. And then, of course, you can go on once you've assimilated data and make a new forecast. Actually, probably at multiple different lead times, but here I've just shown one. You assimilate again, and so on and so forth. And this is sort of the standard pipeline for operational forecasting center. There's one other step to get the products that you find on your desktop or your phone. There will be some post-processing. This might involve running a local area model over, say, the UK, or it might involve doing some statistical post-processing where you correct for biases and incorporate forecaster input as well. And that's what gives you the products that you have on your phone. Okay, so that's how medium forecasting currently works. What happened a couple of years ago was that actually a paper from Ryan Keisler appeared on the archive. So Ryan was a physicist who in his spare time decided to apply modern, actually graph neural networks to weather forecasting. And then this got picked up by both Huawei and Google, who looked at replacing the forecasting step of this pipeline with a machine learning model. And what they did was actually the same as what Ryan did. They took this amazing data set called Error 5, which is actually produced by ECMWF, from which I'm showing some animations of here, which contains humanity's best estimate for what the atmosphere has done over the last few decades. Actually, they took the last 40 years of this data set, so living in the sort of satellite era. And this data set contains large numbers of variables, some of which I already talked about, like temperature and pressure, but actually other variables in here on a fine grid, again, around the world. Here, the grid boxes are a bit bigger. There are 25 kilometers in the version of Error 5, which was used by these teams. And they very simply took in one snapshot at Error 5 at one time point, ingested it into the machine learning model, and then predicted what would happen 6 hours into the future. And they trained the model to predict the outputs exactly like we're seeing through in this animation here. So this is a big machine learning challenge. It's mainly an engineering challenge, actually, because these data sets are so big. If we take the higher res data sets, a single data point here can be about 3 gigabytes big. So if you compare this to things like language models, where each data point is like a passage of text, it's maybe a few hundred bytes, or maybe a bit larger than that, but it's certainly not megabytes or kilobytes or gigabytes. Here, instead, we have much larger data points. So fewer of them, but much larger, and that brings with it like huge engineering challenges. And perhaps one of the most impressive things they did was to develop a pipeline for training these systems that could truly scale. And a paper simultaneously more or less came out in Nature, and then one very quickly following it in Science, which were the result of these two teams' work. So first the Pangu paper came out, and very quickly after it the GraphCast paper. For reasons that I won't go into, the comparisons in those papers to ground truth were a little bit flawed. And so what I'm going to actually show you are the results from the European Centre for Medium Range Weather Forecasting's efforts to try and benchmark actually the Pangu model, but we get very similar results from the GraphCast model. And they benchmarked importantly against observational stations actually here in Europe. So they said, you know, as a function of lead time ahead measured in days, how accurate in terms of root mean squared error are the predictions coming actually from the Pangu model. And as a baseline, they used the current world's best system, which is ECMWS IFS, or at the time, HRES system. And they compare it to the Pangu model, and for many parts of the sort of lead time horizon here, the two models were very, very similar, and actually at slightly longer lead times, Pangu was perhaps fractionally better. But I think the message from this analysis from the European Centre for Medium Range Weather Forecasting is that the results held up in the Nature paper, essentially, that these models were pretty good, and it was time to get excited about the role that AI might have to play in medium range weather forecasting. This shows the winter. The AI models, for some reason, are all a bit better actually in the winter, and they're a bit worse in the summer than, sort of relatively speaking. Pangu was roughly equivalent to the IFS system. GraphCast was actually a bit better when they carried out the comparison on the GraphCast model from DeepMind. Sort of the killer statement, though, is that Pangu is about 10,000 times cheaper computationally than the IFS system. So the performance is about the same, but the compute overhead is much, much, much lower. And that's really what got everyone excited. Okay, so that's sort of the context. That's where, you know, I entered the picture. We were really interested in these models, and we were wondering about how we could sort of push these ideas a bit further. And so actually the first piece of work that I was involved in this space was an effort inside Microsoft to take exactly the same ideas that GraphCast and Pangu had applied to medium range weather forecasting and see whether they would apply to other parts of the Earth system. And we were interested in atmospheric chemistry and air pollution. Think back to these, you know, large air pollution events in India and indeed China, where we need these better predictive models. We were interested in ocean wave forecasting, which is really important for predicting coastal damage, or for supply chains, etc. We were interested in tropical cyclone forecasting. So one of the big questions about machine learning models is not their average case performance, because we're not really that interested in average cases. We are really interested, of course, in their performance on extremes, and that's really where we need these systems the most. So, you know, what more important event is there than looking at tropical cyclones, and particularly predicting the tracks of tropical cyclones. And then finally, we actually looked at high-resolution weather prediction, so very, very fine grid boxes up to the 10 kilometers that the physics models are currently operating in ECMWF. And I'm not going to talk much about this here, but essentially the story was just the same. So in many of these domains, we have far less data, actually. We don't have the equivalent of this error 5 data set. And so there was some question about whether the machine learning models would cope with that restricted amount of data. And we used a fine-tuning approach where we pre-trained on lots and lots of data to start with, including actually climate simulators as well, that sort of fantasized imaginary weather. And then we fine-tuned on the downstream data sets like ECMWS CAM's model for atmospheric chemistry and air pollution, or their WAM model for ocean waves, or their IFS HRES system for the high-resolution weather. And what we found in each one of these cases was that the foundation modeling approach was, again, competitive with these existing physics-based products, but again was hugely cheaper. So in the case of atmospheric chemistry and air pollution, for instance, it was actually 20,000 times cheaper than the physics model, because the atmospheric chemistry equations are very stiff and require very, very fine time steps to simulate them accurately. So foundation models are starting to play a role in this space, but there's a big elephant left in the room. And the elephant in the room is something I've already alluded to, which is that although these models, and I include Aurora now in this, have looked at reproducing or replacing this forecasting step of weather prediction, in order to actually implement these things and deploy them operationally, you still need this initial state out here. And that initial state requires that you run a simulation, and a simulation relies on you having this physical model and a big team, and is extremely expensive because it essentially involves like backpropping in the machine learning parlance back through the simulator. So you need to almost pass gradients through this big physics-based model, so incredibly expensive. And so the sort of the hubris in GraphCast, Pangu, and indeed our own Aurora paper is perhaps slightly misplaced because we've only replaced one of the steps and we will still require all this infrastructure to run it. You still can't run it in many countries in the global south. It's still slow to innovate, et cetera, et cetera, et cetera. And that was the question that we sought to address in the Aardvark project. And we realized this actually quite a long way out, even before Pangu or GraphCast had actually arrived, that really the sort of the machine learning solution to this is to do everything within a single model. So like do end-to-end forecasting. So that means ingesting the radio sonder, the data from ships, planes, observational measurements at weather stations, and the remote sensing data into a machine learning model that operates and takes in that sort of diverse multimodal set of data, directly forecast ahead. Actually, we looked at forecasting ahead 10 days, and importantly, does the post-processing as well. And if you could do that, you could then optimize the whole thing end to end to be better at, say, predicting the weather in Cambridge right now, or Cambridge over the course of a year. And the whole system could be optimized particularly for that task, which might provide benefits. It would also be much faster because we've replaced the assimilation step, which was expensive, and maybe we could take these things out to the global south. But there was a big challenge. And the big challenge was that the previous success for these models had been based on amazing work that the community had done in this space to get their data ready. And ECMWF and indeed GFS, the system from the States, had all gone to great lengths to make their data publicly available. It was clean, there were no privacy issues, there were good APIs for accessing it, and that really meant, unlike many fields, everything was machine learning ready. And all Ryan Keisler had to do in the weekend was like download the data set and plug it into a standard machine learning pipeline. Most of the work actually had been done by that huge body of people beforehand, and the machine learning community owes them a huge debt. This is not the case if you want to do this. So in particular, these data which go into the best physics-based systems are scattered throughout the world and across the internet. It's not something that they can provide because they don't own that data. They come from China or India or the States. And so Anna Allen, the lead on the Aardvark project, spent literally 18 months scouring the internet, making connections, and accumulating the nice machine learning ready data set that's necessary to execute on this. So this involved collecting up a whole bunch of sounder data. So these are passive instruments in the atmosphere that monitor various spectral bands of reflected radiation. We have scatterometer data, so these are really important instruments that send out directed radiation and measure scattering off, for instance, the oceans, and that's really important for detecting implicitly wave height and tells you about the velocity of winds close to the surface of the ocean. And we have a bunch of geostationary instruments here that have been consolidated with this GridSat and SEVRI products. And then at the bottom here, we have the in situ measurements. So everything up here is satellites, and by far the largest data set here, or the largest data source, are these remote sensing instruments. But importantly, we have at the bottom here weather stations, about 10,000 weather stations from the HAD ISD data set. We have data from machine platforms, from marine platforms like boats, and we have radio sonder data in this IGRA data set as well. So everything needs to be collated, cleaned up, and aligned together. And one of the sort of the outputs of the Aardvark project is a nice curated data set that other people can use. So a heroic effort, lots of great work had gone in there, and now it's sort of machine learning ready to be deployed in the Aardvark model. So the second big question we faced was, how should we structure this model? So unlike the case for modeling error 5, where you have a nice grid coming in and a nice grid coming out, This is a much messier situation. So as you'll have seen from these plots here, for instance, the in situ measurements happen at particular locations. They don't live on a nice grid. They're just measured at particular locations. The satellite data often has these swaths in it with big areas of missing data again. And so you can't use off-the-shelf machine learning methods to process this data. Instead, you have to build something a bit more bespoke that takes this messy multimodality off the grid data. And I'm going to say one or two words about that in a minute. And I'll have one slide on the methods. Just in terms of time, do you know when I should be aiming to end for, by the way? 5 minutes. Yeah, great, thanks. So first off, we build an encoder, and the encoder takes these multimodal data and outputs the current state of the atmosphere, a bit like a simulation. Then we apply a processor, and the processor, you can think of it very much like a GraphCast or Aurora or a Pangu, which just takes the previous state of the atmosphere and evolves it actually one day in the future in our model, but it could have been 6 hours. And then you can roll it out by applying that same model multiple times to get to different lead times. And then finally, we apply a decoder, which takes the current state of the atmosphere and outputs predictions at actual specific in situ stations, like the weather stations at the bottom. We use a convolutional neural network for that part. In order to train these things, the encoder takes in the raw data, and then we target error 5. So again, we're going to use error 5 in training and numerical weather prediction in training, but we're not going to use it when we deploy it at test time. We'll be totally free of NWP at test time. We train the processor just like we trained Aurora, Pangu, and GraphCast by training it on error 5. And then finally, we apply the downscaling model, and the downscaling model was trained by taking in error 5 and targeting the raw observations at the in situ weather stations. And then finally, we can compose everything together and fine-tune the whole thing end to end. So that's the way we're going to build the model. I'm not going to have time to tell you much about the underlying structure, but I've got some slides here if someone wants to ask a question about it. So this is the machine learning model that we're going to use in order to take messy off-the-grid data at the bottom and end up with a nice predictive model which will include uncertainty in it. And it leverages a family of models called neural processes, which my group had worked on previously for 3 or 4 years, that could handle this missing data and give you nice, well-calibrated uncertainties coming out. But within the interest of time, I'm just going to hop over this, but I can come back to it and show you the results of the system. So on the left, I'm going to first show you Aardvark's predictions. This is for wind. On the right, I'm showing ground truth across the globe. And this is at t=0 days. So this is kind of just doing a simulation, estimating the current state. And here's what happens as I forecast forward 2 days to 3 days into the future. You can see that the Aardvark system gives pretty good estimates of the macro scale structure in here. It misses out, like many of the machine learning models, fine-grained detail. And that's a problem in general with the AI models, which has actually started to being fixed by a new generation that actually use probabilistic models like diffusion or CRPS in order to generate the fields. But at the time, we didn't use those techniques, and so this ends up looking a bit blurry. Nevertheless, we managed to pick up this tropical cyclone, Birgitta, which is off the coast of Madagascar and caused 100 million pounds in damage in Mauritius and Reunion Island. And it wasn't really obvious that that was going to happen from the initial condition here. If I wind back, the tropical cyclone develops through this period, and the model is still able to sort of correctly predict it's going to happen. I'm not going to talk much about the gridded forecasts, but here's a comparison of the gridded forecasts on multiple variables like temperature, wind speed in different directions, and things like humidity at different heights. The important thing to note is the following. We've compared to GFS, which is the sort of the best American system, and sometimes Aardvark is a little bit worse than the best American system. Sometimes it's a little bit better, but you know it's kind of roughly on on par for many of the variables. And this genuinely is 10,000 times cheaper, and I can run this on a desktop computer in my office, whereas GFS requires a supercomputer. We still lag behind ECMWF's HRES system, so there's some work to go to become truly state-of-the-art here, and you would be giving up some performance if you used it. These are the station forecasts. So this is when we predict down to actual specific locations in the world. And again, we're comparing Aardvark here in this magenta color to IFS ECMWS system, and we've done a little bit of downscaling to make this comparison fair. In many regions of the world, we're on a par with ECMWS system. Importantly, in places like West Africa and maybe the Pacific, where numerical weather prediction doesn't work too well because much of the weather is driven by convection, which is hard to model, and the models are too coarse to capture it. There are big differences between our approach, which is doing pretty well, and say the HRES approach. Depends a little bit on the variable, but sometimes there are large gaps. And in fact, we quantified the effect that this end-to-end fine-tuning has in these areas. So this is the additional benefit from optimizing the whole thing end-to-end. And particularly on temperature, we often see big benefits from this, like 6% improvements across multiple regions. For wind speed, it was a little bit lower, say 1%. But to put this into perspective, the last 18 months of development of the IFS system it caused their system to improve by roughly 2%. So anything around 1% or 2% is fairly chunky in performance improvements that are well worth having. I should say that we admittedly start from a lower baseline than those physics-based models. What are we doing currently? Well, one of the exciting things we're doing currently is we're hooking these things up, as I guess the world is, to LLMs. And so we're sort of, in this example, generating actually a forecast report, a meteorological forecast report for the New York area back in April, using directly satellite weather station radio sonder inputs, and we've trained this on a whole set of meteorological reports. And in the future, we imagine having an AI agent that you could interact with that knows about the weather, that can maybe give you business advice if there's a flood in your area, and what insurance you should take out, and what you do to your suppliers, etc., etc. So, bringing all the advances in foundation models to this space. Okay, I want to end by just thanking the Aardvark team. In particular, the two first authors, Anna Allen and Stratis Marco, without which this work definitely wouldn't happen. ECMWF, in particular, Matt Chantry, were amazingly helpful and also on the paper, and we wouldn't have managed it without him. And then I wanted to highlight Will, who's at the back of the room, who did fantastic work on the downscaling, if you want to chat to him, and Scott, who's going to talk later, I think, about really interesting things like what have these sorts of models got to say about climate, which I think is one of the huge unanswered questions in this space. Here are the references to the paper. There's kind of a nice end to this story. Look, both of these papers came out in the same issue in Nature early in this year in May, I think. I should say that underneath the surface, things were way more chaotic than this talk suggests, and it was like the most turbulent time in my professional career. And one thing you shouldn't take away from this talk is that everything was easy, and that these results were easy to come by. It was an incredibly hard effort in both of these cases, which almost broke us. So we were really pleased that there was like a happy ending to this story. Thank you very much. Sorry for running slightly over time.
Do we have any questions? Yeah.
You're saying that Aardvark replaces the entire process with an end-to-end system. It seems like the architecture you suggested has a data assimilation stage, a processing stage, and a fine-tuning stage.
Yep.
Is the benefit of this the fact that you can fine-tune it all in one go? Or,
yeah. So the benefits are multiple. So if you don't have a machine learning way of doing a simulation, you're still going to have to rely on the physics-based model, right? So even if the whole thing is not end-to-end fine-tuned, you still get a big advantage in terms of computation for having a machine learning module that does the assimilation. So that's one advantage. And yes, then the advantage is you have a differentiable way of doing a simulation. You can compose that with other models and now fine-tune the whole thing as well. So I sort of see those as two different, different benefits. Does that make sense?
Yeah.
Yeah, Christian at the back.
Hi Rich, great talk. Is it important in your view that we understand why the system is behaving and evolving the way it is, and where does that come into this end-to-end forecasting as well?
Thanks, Alex. So I should say, Alex, I missed him off. I didn't realise you were going to be here. So Alex was also one of the co-authors on the paper, was instrumental for the atmospheric chemistry results. So he should have been on the list. Apologies, Alex. I think that's a really interesting question that we could have an excellent discussion on. So, and probably don't have time for the full discussion here, but maybe give some context. So, Jeff Hinton, when you ask him about interpretability, he's like, we shouldn't really care about interpretability. Like, it's going to be impossible to actually work backwards what the machine learning system is doing. And in particular, one of the things the machine learning system is doing is not just becoming a physical emulator, because many of the variables here are implicit or latent. And they're latent for a number of reasons. We use coarse-grained inputs. We miss out a whole bunch of the variables that are in error 5, like we don't have an ocean model that's coupled in there. We don't do the coupling to sea surface temperature properly. So there's things there that the system has to estimate. And indeed, the data we train off is observationally driven. So it comes from, at least partly from observations, and there are a whole bunch of latent processes there that are not well characterized. So the system, when it predicts forwards in the future, has to do two things. Firstly, it has to do inference to estimate what is going on with those latent variables and do a bit of pattern matching. And then once it's sort of estimated those variables, then it can do the physicsy-based thing. And that pattern matching thing is A, hard to interpret, B, it's not physical. So if you impose physics-based constraints, you would stop the system from doing inference, and in fact, you'd make the system a bit worse. So I think we sort of need to think deeply about what we want to do about that, and I think we need like a new machine learning paradigm to do physics-informed machine learning that doesn't stop these systems from doing this inference pattern matching stuff, which gives them lots of their skill advantage over the physics-based systems, but at the same time allows us to put in these physics constraints where they're useful and helpful. I should say ECMWF are not worried about this at all, because I go and talk to the the people writing IFS. And I'm like, well, your model is interpretable. And they go, no, it's not. We've got code there that's from like 20 years ago, and no one knows what it does. And occasionally it breaks, and we have to phone people up and desperately fix it. And so IFS isn't actually that interpretable in the first place, which I think is another interesting discussion to have.
Okay, I think given time, we'll now move on to the next talk. But as I mentioned, that there should be a bit of time at the end of the session for any additional questions for Richard. So if we just thank Richard again. And